Well, thank you so much. Thanks for inviting me to talk here and give a talk on the Krafla Magma testbed. I assume you see the screen now. So my name is Hjalti Ingólfsson. I'm the general manager of Georg, which is a geothermal research cluster in Iceland, and we are also taking care of the project office for the KMT project, and I'm titled the Chief Project Officer of that project. The origin of the Krafla Magma testbed is definitely from the ITTP one, as Guðmundur Ómar had already showed you a bit on that, and we are looking at the Krafla area for this testbed. You can see the location of the Krafla area on the map of Iceland. It's here in the northeast, and of course, right on top of the boundaries of the crustal boundaries, where the crust is going to east and west. You can see here the yellow line of the caldera, assumably the Krafla caldera, and then the dotted line here is what we foresee as a rhyolitic magma. On the side here, you can also see a schematic of how we foresee this. So this is the Krafla magma testbed magma body we would like to enter into. Of course, I would be probably preaching to the choir, telling people the importance of magma for Earth and for the crust and all that. Of course, magma is forming the Earth crust. It produces volcanoes and therefore also hazards to people and to infrastructure and buildings and so on. And it also is generating the heat for the geothermal energy. So it is, of course, very important topic to research and to understand better. Until now, we have basically been looking into magma from three ways. You know, this is a schematic of or a diagram of how to enter magma. So we are here standing on the surface of the Earth. We have a scale here of temperature going up to 900 degrees, and then a scale here of depth going down into the crust. So, and magma is sitting in the crust here quietly, and there are basically three ways to get to that crust. You can either wait for it to erupt. You take and then take samples of the magma on top of the Earth crust, and of course that cools down and it's exposed to the atmosphere and depressurized and so on. So it changes, it alters in that process. We can also wait for a very long time for the magma body basically to be erupted up to the surface and check fossil magma bodies either at the surface itself or core existing magma bodies that have been sort of crystallized or cooled down. That of course takes time, and again it alters, it changes. And then the third way is just basically just to drill it in the crust where it's sitting quietly, like we want to do in the KMT project. So how to drill a magma? Of course, that's not simple, but it's in fact it's the idea is quite simple though. We just have to cool it. We just have to drill down kind of a conventional geothermal well down to the roof of the magma, to say so, and then cool it down. And the idea we are going to do is to core through the boundaries of solid rock into the magma body itself, with of course a continuous cooling. And we are doing and will be doing some modeling on how fast we need to, or how slow we could say, need to drill into the body so that will cool significantly or sufficiently before drilling it. And also how long we have to cool it so that we can draw the drill string up again and possibly place some measurements tools within the socket or the sock that we create with drilling into the magma before it closes up again. This has been done before, of course, like Guðmundur Ómar also already told us in Krafla, where people accidentally drilled into magma without too much risk. This has also been done in Kilauea in Hawaii, where drill string or where it was drilled into a magma pond or a lava lake, which was kind of a proxy to magma, but not exactly like magma. But it showed that it could be done to quench magma or molten rock during drilling and get sufficient cores to study. So this is what we want to do in the Krafla magma testbed. Guðmundur Ómar has showed you this before. Of course, all started with the IDTP-1 project, where the engineers drilled into magma accidentally or without knowing the magma was there, and they got some chips from the magma itself, realizing that what they had were fighting for or fighting with, and that's actually gave us the opportunity to do what we want to do. There were some big surprises in this process, of course. This magma pocket that they drilled into was not seen by common sort of geophysics at the time, at least. And they did not see it coming. They knew about magma chambers around there and wanted to drill close to it, but did not see this magma itself. So that's something that is worth studying to understand better how to see magma pockets like this. It was very shallow at 2 kilometers depth, so it's relatively easy to get to again. Don't have to drill so long. The area there was very liquid rich. There was a complete loss of circulation during the drilling, and it turned out to be very hot and very high energy around this area, giving it a very good possibility to harness this magma energy. Another very interesting finding was that there was no crystal. It was not a crystal-rich magma that came up. The chips were not crystal-rich. So, which poses the question: is the models that are sort of predicting with magma chambers like this or magma pockets like this wrong? Is the magma possibly convecting within the system there and not only cooling down for a period of time, but could be kind of a live magma chamber that could continue to be there for thousands of years. There was a high permeability around the magma chamber, possibly because of thermal cracking. And then, of course, as I said before, a very good source for heat extraction and to use that as such. It was a rhyolitic magma and not a basalt. So possibly this is, a lessons on the evaluation of the Earth's crust. Maybe Iceland is resembling the early Earth or young Earth, which is also very interesting to understand and study. And last but not least, there might be many more magma pockets like this under other volcanoes around the world that could be extracted, that could be a source for energy extraction, and it could also be then a very, very interesting system for magma energy, and of course to monitor magma as a whole with all that potentials. So the opportunity we have in front of us is therefore we know of a magma chamber relatively shallow in the Earth's crust, sitting there quietly. We want to understand why it sits there and how we can extract energy from it, and how we can also monitor and understand better how the magma behaves, and possibly understand also the signal it is giving to the surface, kind of calibrating measuring equipments or the monitoring equipment that we have for volcanic hazards. So in this test bed, we want to combine basic science, basic earth science, volcano monitoring, and geothermal energy, and it all evolves around the magma chamber itself. And the objective is, of course, scientific, it's public safety, it's economics, and then technology. So a scheme of the big dream in Krafla is to then create a international magma testbed. So we would like to drill down to magma. First of all, into the magma itself. That would be the proof of concept borehole to drill down to magma. We also would like to have more wells around the area, drilling down to magma, not necessarily into it, and then possibly under the magma pocket. We want to have surface and boreholes, geophysics and geochemistry measurements, satellite and INSAR measurements on the surface and in the air around it. We would like to use the existing geothermal infrastructure to even get more information about the system and use boreholes for collaboration and so on. And we hope to be able to set up a facility on a site or close to the site for laboratories and visitor centers and technology centers to study magma and to gain knowledge on the system. And the idea is to have there an international infrastructure that can be open to scientists and engineers and all around the world to come and do their studies. This is, of course, a big undertaking, and we have decided to divide it down to several steps. And we are starting now in the preparation phase, which we call KMT0, which is preparing for the first drill, the proof of concept borehole, where we would drill down to magma or into the magma chamber itself, and then gradually increase the activities there until we have an open facility to invite scientists, as I said, to do their tests. In these phases, of course, we will learn by every step more about the system itself. We will pose or set up research questions, which will be prepared in the preparation phase, exactly what we want to get out of the first borehole and how do we want to have kind of a science plan into the future, how to utilize this facility the best possible way. This also shows here indicative cost of the operation, and the first preparation plan is about 5 million, and then 25 for the first drill, and so on and so forth. And for the whole area or for the whole facility, we foresee at least $100 million investment. So it's a quite a big challenge. For the preparational phase, for the phase 0 phase, we have already some organizational structure. We are looking into two very important parts in the preparation. This is part A, which is the governance and stakeholder engagement, to understand how to set this up, how to create the governance and how to set up a business plan for this infrastructure facility for the long run, and how to engage with stakeholders, local community and the global community on that sense. And then part B, which is equally and possibly more important, is to develop the technical and science planning to do this, to prepare or design the pathway, the drilling down to magma, select materials. Of course, like has been said here before tonight or today is the challenge of the casings and the cementing, to have that all in line and prepare for this actual drilling. And then the earth science and reservoir and data management system to be ready for this endeavor. So we are starting this now, and we hope to be able to start drilling in about 2 to 3 years time from now. We have a strong international cooperation ongoing here, high quality consortium, about 38 institutions, research institutions and companies from 11 countries have shown interest and want to collaborate with us on this. We have had strong support from the Icelandic government, both in written terms and also some financing in the startup. So Icelandic government is going to be a founding member of the KMT infrastructure facility. So we have already received some funding to start the preparation from the government in Iceland. We also have acquired a grant, or got a grant from the ICDP, both on the preparation and then on the drilling when that comes in. So that's a very significant step to get that proof, by financial support, of course, but not less the scientific proof that this is a sound project and wise to do this. And then we are under negotiation with NERC in the UK and RUNIS in Iceland for funding this preparation phase. So we're very close to finalize funding for this first 5 million step of the preparation. Of course, international cooperation is very important, but equally important is the local community. And we have been in very good connection and cooperation with the local community and in the north, in Krafla area and around Miva. And we have received a very positive reaction there, and we are looking very much forward to continue that and set this all up. So that's about it for now. A very quick overview. I want to draw your attention to a YouTube video that explains the KMT project a bit more. This was a video that was created for the AGU conference in December, and you can find this under this link there. That's about it. Thank you very much for the opportunity here, and I'm happy to answer any questions you might have on this.
Thank you. Very good overview. Thoroughly enjoyed it. Looking forward to the next steps, when you get the $5 million and then start drilling wells and we start learning. I have a question from Pat. Given that Krafla was the site of lava erupting through an existing geothermal well, and that can't have been IDDB1, it must have been an early one, I assume. What steps could be taken to make sure that this doesn't happen for the KMT wells?
Well, this actually was much earlier than the IDDB1. This was in the Krafla fire itself, where basically there was an eruption ongoing, and it tended to be through one of the wells. Of course, in IDDP there was they drilled into magma and they got a kick, like Guðmundur Ómar explained. They got kicked to the drill string, explaining a bit that magma was forcing its way a bit up the well, but it did not reach the surface or anything, and we believe that this will not happen for us either. However, we are doing and will be doing a risk mitigation effort or risk assessment on how to do the drilling properly, and but evidence show that drilling a pocket like this is basically not threatening to start an eruption or anything like that. So
excellent. Yeah, I had a quick question which was about Obviously, the KMT is as a testbed is in your setting is looking at a rhyolitic body above basically basaltic volcanism, and in Hawaii it was, I assume, basaltic magma that was drilled into, so a different type of magma. I'm wondering, is there any preferred magma from the modeling studies that in the future one would look at from the point of view of exploring for magma hosted energy systems? Is there any of those types preferred?
I'm not the expert on this myself, but I think that there are some evidence showing that a magma body or rhyolitic magma body like this could be sitting within the crust in different places in the earth, and there must be a reason why it's sitting at 2 kilometers depth. This has been shown also in other places where people at least think afterwards that they have drilled into magma before exactly at the same depth, a rhyolitic magma like this. So I would think, it's just my assumption, that a rhyolitic magma body like this would probably be the best sort of way to extract energy from, because it at least seems so. But of course we don't know yet, and this is one of the big questions that hopefully this project will help us to understand.
Yeah, I'm guessing that gas content might be quite a crucial component of the risk assessment. Pat corrects me and says Hawaii was dacite, not
okay.
basaltic. So that's interesting. Yeah, so thank you very much again, and we'll move on to the next presentation.